Hello, welcome back. In this video, we'll discuss about hybridization. Here we'll learn the concept of hybridization in detail. You know, in order to explain the geometrical shape of methane, ammonia, water, Pauling introduced the concept of hybridization. According to Pauling, the atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals, and the hybrid orbitals are used in bond formation. The phenomenon is known as hybridization. You see, according to Pauling, the atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals, and the phenomenon is known as hybridization. Here, the hybrid orbitals are used in bond formation. Hybridization can be defined as a process of intermixing of atomic orbitals having nearly same energy so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. So hybridization can be defined as a process of intermixing of atomic orbitals having nearly same energy so as to redistribute their energies, resulting in the formation of new set of orbitals having equivalent energies and shape. Example, when 1 2s and 3 2p orbitals of carbon atom. Here the 2p orbitals are 2px, 2py and 2p. When 1 2s and 3 2p orbitals 2px, 2py and 2pz of one carbon atom get hybridized, form new sp3 hybrid orbitals. You see, carbon 6 in ground state, 1s2, 2s2, 2px1, 2py1, 2pz0. This is in ground state. When 4 H atoms will form 4 bonds with carbon, carbon will be in excited state. So 1 2s electron will jump to 2pz, and the configuration will be 1s2, 2s1, 2px1, 2py1, 2pz1. Here you see, this is the ground state and this is the excited state. And in excited state, you will find 4 half-filled orbitals. And here 1 2s electron will jump to 2pz. And we can explain this part diagrammatically also. You see, here 1s2 means a carbon nucleus is there. Above the nucleus you will find 1s, then above it you will find 2s, then this is 2px, this is 2py, then 2pz. In presence of 4 H atoms, means 4 1s orbitals, this carbon get excited. This is the ground state. In excited state, you see 1s will not take part in hybridization. 2s and 2px, 2pi are present in valence shell, they take part in hybridization. So here the green color 2s, you see this green color 2s is like this, and it will become like this. Here is the nucleus at the center, and the nucleus is over here. I have made it yellow in the ground state, so let it be yellow. Then 2px, nucleus is at the center, 2px becomes and the nucleus is at the, then the red color 2py, red color 2pi becomes and the nucleus is over here. Then 2pz, and the nucleus is over here. You see, this green color, one is 2s, one is 2px, red color one is 2py, this one is your 2pz. During hybridization, the shape of the hybridal becomes like this. But you see, they have a common nucleus. They have a common nucleus. In all these four cases, the nucleus is same. So we cannot draw four different hybridals. And this is your positive one, this is your negative, positive, negative, positive, negative. The bigger one is positive, the smaller one is negative, and they have a common nucleus. So let me make a diagram like this. This is the nucleus. The green color will be like this, then the blue color one like this, then the red color one, then you see there are as 2s, 2px, 2py and 2pz take part in hybridization. So each hybridal is known as sp3. sp3, sp3, sp3. sp3, sp3, sp3. You see here, when 1 2s and 3 2p orbitals of one carbon atom get hybridized, form 4 set of sp3 hybridals. You see, this is the diagram I have drawn over here. Now the salient features of hybridization: number of hybridals is equal to number of atomic orbitals that get hybridized. You see, in this case 2s, 2px, 2py, 2pz, 4 atomic orbitals are there, and you got 4 sp3 hybrid orbitals. Just I have explained here. Here you see 2s, 2px, 2py, 2pz, 4 orbitals in valence shell. During hybridization, this 2s, 2px, 2py, 2pz get hybridized to form 4 set of hybrid orbitals, and these are hybridizing orbitals. These are hybridizing orbitals. So number of hybrid orbitals is equal to number of atomic orbitals that get hybridized. These are also known as hybridizing orbitals. Hybrid orbitals are equivalent in energy and shape. Here all these four hybriditals are equivalent in shape and energy. Equivalent in shape and energy. Hybriditals are more effective in the formation of bonds. The hybriditals are more effective in the formation of bonds than that of pure atomic orbitals. Here you see this is suppose 2s and this is one of the sp3 hybridital. So this sp3 hybridital can form a better bond than this pure atomic orbital, or you can say effective in bond formation, or you can say sp3 is more effective in the formation of bonds than this 2s pure atomic orbital. After hybridization, the hybriditals are directed in space in some preferred direction to have minimum repulsion between electron pairs to form a stable arrangement. So type of hybridization indicates the geometry of a molecule. Here you see, here in this diagram, these four sp3 hybriditals are directed in space in four different directions, and the shape is tetrahedral. After hybridization, the hybriditals are directed in space in some preferred direction to have minimum repulsion, because hybriditals also carry electrons, so they repel each other. To have minimum repulsion and maximum stability, they remain far away from each other to form a stable arrangement. So type of hybridization indicates the geometry of a molecule. Conditions. The orbitals present in the valence shell of the atoms are hybridized. The orbitals present in the valence shell, here I have told you the orbitals present in the valence shell, take part in hybridization. The orbitals present in the valence shell of the atoms take part in hybridization. The orbitals present in the valence shell of the atom are hybridized. The orbitals undergoing hybridization should have almost equal energy. So 2s and 2p has nearly same energy. Promotion of electron is not essential condition prior to hybridization. In case of carbon, the ground state is 1s2, 2s2, 2px1, 2py1, 2pz0. During hybridization, one 2s electron will jump to 2pz, and the configurations in excited state will become 1s2, 2s1, 2px1, 2py1, 2pz0, 2pz0 becomes 2pz1. But in case of nitrogen, 1s2, 2s2, 2px1, 2py1, 2pz1, what happens? There is no 2d. In case of nitrogen, there is no 2d. So 2s electron cannot jump to higher orbitals. So in excited state, the configuration will be 1s2, 2s2, 2px1, 2py1, 2pz1. This is the ground state, this is the excited state. In both cases, you'll find the electron configuration is same. So promotion of electron is not essential condition prior to hybridization. In case of carbon, one electron from 2s will jump to 2pz, but in case of nitrogen, 2s electron cannot jump because there is no vacant 2d. Half-filled orbitals and in some cases filled orbitals of valence shell take part in hybridization. Half-filled orbitals and in some cases filled orbitals take part in hybridization. In case of carbon, excited state 1s2, 2s1, 2px1, 2py1, 2pz1. Here all the orbitals are half-filled, they take part in hybridization, no problem. But in case of nitrogen, in excited state 1s2, 2s2, 2px1, 2py1, 2pz1. You see here these 2s, 2px, 2py, 2pz, they all take part in hybridization, but here 2s is fully filled. Here 2s is fully filled. Here 2s is fully filled. Though it is fully filled, it can take part in hybridization. 2s, 2px, 2py, 2pz. So half-filled orbitals and in some cases filled orbitals like 2s2 in nitrogen of valence shell take part in hybridization. Types of hybridization: sp3, sp2, sp, sp3d, sp3d2, sp3d3. Let us explain the type of hybridization, in CH4. You see, in CH4, the central carbon gets hybridized. Here you see carbon is at the center and 4 hydrogen atoms are on the 4 different sides. So you can say carbon has 4 electrons on the valence shell, and 4 electrons on 4 different sides will form 4 bonds like this. So carbon in CH4 is sp3 hybridized. Here the terminal atoms are not hybridized. Only the central atom in the molecule get hybridized. Carbon 6, 1s2, 2s2, 2px1, 2py1, 2pz0. It has 2 half-filled orbitals, but it can form 4 bonds. So this is possible because of hybridization. So carbon 6 in ground state is 1s2, 2s2, 2px1, 2py1, 2pz0. But in presence of 4 hydrogen atoms, carbon becomes excited. So in excited state, the configuration will be 1s2, 2s2 becomes 2s1, 2px1, 2py1, 2pz. 1 2s electron will jump to pz. So here it is 2pz1. This is the electron configuration of the ground state and excited state of carbon atom. Now it can be diagrammatically shown. Here you see, already I have discussed. Let the carbon nucleus is in green color. Above the carbon nucleus you will find 1s. Then above 1s you will find 2s. Then this is 2px. This is 2px. This is the nucleus. Then this is 2py. Then this is 2pz. In presence of 4 H atoms, this carbon in ground state get excited. For information, 1s will not take part in hybridization. So 1s is here in white color. So the yellow color 2s, will become like this. And here the nucleus is over here. This one is the positive lobe, this is the negative lobe. Then 2px will become like this. You see, this is positive, this is negative, this is the nucleus. Then the red color 2py will become like this. This is positive, this is negative, and this is the nucleus. Then the last one becomes like this, and this one is positive and this one is negative. But we cannot draw like this. Why? Because they have a common nucleus. So here we have shown 4 nuclei. It is impossible. Here you see there is one nucleus. They have shown 4 nuclei. So it is impossible. So for the ease of understanding, I have shown all hybridizing orbitals in hybridized form. And for information, this is 2s, 2px, 2py, and 2pz of carbon take part in hybridization. As there are 1s and 3p orbitals, the type of hybridization is sp3, and these are also known as sp3 hybrid orbitals. These are also known as sp3 hybrid orbitals. But these 4 orbitals should remain like this. Here at the center you will find the nucleus, and the smaller lobes are like this. These are positive, 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 positive. These are all sp3, sp3, sp3. If you want to see this in this color form, then I can draw again. The yellow color one is like this, then yellow color, then the red color, then the last one. You see, these are sp3, 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 and they have a common nucleus. But these 4 sp3 hybridals stay in a tetrahedral manner. Why? Because electrons present in the hybridal repel each other. So they stay away from each other to have minimum repulsion and maximum stability. But these 4 hybrid orbitals form 4 bonds with 4 hydrogen atoms. These are 1s1, 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 and the bonds are sigma bonds. You see, this is one sp3, this is another sp3, this is another sp3, 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 and on you'll find, so this is carbon, sigma bond, sigma bond, sigma bond, sigma bond. This is sp3s sigma bond, 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 and the bond angle is 109 degree 28 minutes, and the shape is a regular tetrahedral. In sp3, percentage of s is 25%, percentage of p is 75%, s plus p plus p plus p 4. So out of 4, 1 s is there, so 1 by 4 into 100 is equal to 25%. So percentage you got sp3. Let us do another example. Ammonia. In case of ammonia, nitrogen is bonded to 3 hydrogen atoms and there is 1 lone pair. You see the dot structure. Nitrogen has 5 electrons in its valence shell, 2, 5. 3 hydrogen atoms will form 3 bonds and 1 lone pair is there. Now N7, 1s2, 2s2, 2px1, 2py1, 2pz1, 2d is not present over here. So in presence of three hydrogen atoms, nitrogen gets excited. This is the ground state and this is the excited state. In excited state, as there is no 2d or no empty orbital, so 2s electron cannot jump. So its configuration is 2px1, 2py1, 2pz1. You see, the ground state and excited state of nitrogen are same, and you see this is 1s, then 2s, then 2px, then 2py, then 2pz. In presence of three hydrogen atoms, it gets excited. Two s becomes, then 2px becomes like this, 2py, then 2pz. You see, in 2s there are 2 electrons, and in 2px, and in these 3 you'll find 1 in each case. You see, this one is slightly bigger in size, and I can write these 4 hybridals like this. It has 2 electrons, 1 1. This will not form any bond with anyone. This will remain as a lone pair, but these 3 half-filled sp3 hybridal will form bonds with hydrogen atoms. So you will be getting this one is slightly bigger. Here the hybridization is sp3, bond angle should be 109 degree 28 minutes, but this is wrong. Here bond angle decreases from 109 degree 28 minutes to 107 degree. Why? Because this lone pair and this bond pair repel each other. Similarly, this lone pair and this bond pair repel each other, and bond pair repulsion is also there. Lone pair bond pair repulsion is more than bond pair repulsion. Bond angle decreases from 109 degree 28 minute to 107 degree. Bond angle decreases from 109 degree 28 minute to 107 degrees, and the shape is not tetrahedral. The shape is distorted tetrahedral, that is trigonal pyramidal. Let us draw another molecule having pi bonds. For information, pi bonds are not included in hybridization. Pi bonds are not included in hybridization. Let us take an example of carbon dioxide. You see, carbon is at the middle and 2 oxygen atoms are on 2 sides. Carbon has 4 electrons in the valence shell. Oxygen has 6 electrons because its atomic number is 8. Here you see there are 2 bonds, here 2 bonds. This is a sigma, this is a pi. Pi bonds are not included in hybridization. Pi bond is due to sidewise overlapping of p orbitals. So sigma bonds are included in hybridization. There are 2 sigma bonds. As there are 2 sigma bonds, the type of hybridization is sp. You see, carbon 6 in ground state, 1s2, 2s2 to px1 to py1 to pz0. Carbon in presence of two oxygen atoms get excited and it becomes 1s2 2s1 to px1 to py1 to pz1. Here what happens, 2s and 2p take part in hybridization, but these 2py and 2pz that don't take part in hybridization, they form two pi bonds. So here you see this is 2s, at the center you'll find nucleus, then 1s, and this one is 2s. Let it be in white. Then this is 2px, 2py, then this is 2pz. In presence of two oxygen atoms, what happens? 2s becomes like this, 2px becomes like this, but py and pz remain unhybridized. But they have a common nucleus. You see, we cannot write these four orbitals in this fashion. So for the ease of understanding, I have written separately, but now I have to write. So I have to draw the structure as shown. You see, this is the nucleus. This is one sp. Okay, then second one, this sp, like this. So two sp orbitals are drawn over here. Then this one is perpendicular to the axis passing through it. Then this one pz. So this is in excited state. Why? Because two oxygen atoms are present on two different states. But here oxygen is not hybridized. This is also not hybridized. But the atomic number of oxygen is 8, 1s2, 2s2, 2px2, 2py1, 2pz1. So for your information, this 2py and 2pz will take part in hybridization because these two orbitals are half filled. As they are half filled and 2py, you see this 2py, then this is 2pz perpendicular to each other. You see, this is 2py and this is 2pz, this is 2py and this is 2pz. Here you will find a sigma bond, here you will find a sigma bond, but this one will form a pi bond and this one will form a pi bond. Let me draw the structure again. You see, this is the carbon one. Let me draw again. You see, carbon has two sp hybrid orbitals. Then it has 2py and 2pz. This is 2py, this is 2pz. Oxygen has 2py as well as 2pz. sp, it will form a sigma bond. Here it will overlap each other and you will find two electrons. Then here you will find two electrons, pz. Then is a sigma bond, but this is a pi bond. For your information, this is a pi bond, this is a pi bond. Pi bond has two electron clouds, pi bond has two electron clouds. So the structure is like this. Bond angle is 180 degree, shape linear. sp hybridization means percentage of s 50%, percentage of p 50%, Thank you.